Now, the first thing that we really need to understand well to graph semicircles and other formulas that have square roots in them is we need to understand that square roots are actually all positive. Now, this is sometimes a surprise to a Year 11 student, and I think especially to smart students. Let me explain why. If you take this one as an example, the square root of 16 is 4. A lot of you might think, isn't it also negative 4? No, it's not. The square root of 16 is only 4 and not negative 4. But the reason it gets a bit confusing is because in year 7 or 8, when you learn how to solve an equation like this, the answer actually is positive or negative 4. Why? Well, see, here we've got x being a variable. And so when we say what could x be, x really could be positive or negative 4 here, because if you square either of those numbers, you do get 16. Now, when smart kids learn how to do this when they're in year 7 or so, they often leave this step out because they say to themselves, oh, I know, 4 fours are 16. And so they leap very naturally straight to the answer. And they're usually okay with the whole idea that negative 4 times negative 4 is also 16. And so generally bright students will leave this line out. But this line is the one that actually tells us in the procedure here that when we're taking the square root of something, when we're solving an equation, we need to consider not just the positive, but also the negative version of that square root. And if you see that in this line, it makes it a little bit clearer that the square root of 16 really is just 4. We just put the plus and the minus options in there because we acknowledge that a negative times negative does equal a positive number. So it's important that every time we see one of these square root signs, we're thinking to ourselves, the answer to that bit is positive. Now, if we revisit our formula for a basic circle that it's got its center at the origin, then we can see that this thing is not actually a function. It is a relation. Anything you can graph on a Cartesian plane is a relation, but it would fail that vertical line test. In other words, a vertical line would cut through this thing at some places twice. So if we want to write this thing as a function, then we need to limit it somehow so that it actually will pass that vertical line test. Now, we also know that the formula here doesn't really look like a function. Functions we're used to seeing as y equals something, or f of x equals something, where we have all the xy stuff on one side and the y sitting all by itself on the other. So if we were to manipulate this and get it looking a little more like that, we can see that we could subtract y squared from both sides here, and we would have this. Now, this is still the exact same circle. But if we were to say, well, what would happen if we took the square root of both sides? Then we would have just y. Would this still be our circle? Well, if we put a little plus and a minus out the front, then yes, it would still be our circle, because y now could be negative or it could be positive. And this are the exact same thing. It's actually our circle. But if we take away the option to be positive or negative, our definition that all square roots are positive now says, hey, this is a lot like our circle, but if everything here is positive, then if y is equal to that, then y must also be positive. And that means that this whole section of the circle is no longer possible in that formula. And so what we effectively have here is just that top half of the circle, and we'll call that a semicircle, semi meaning half. It's literally half of the circle. Now, if we want to draw the bottom half of the circle, then it makes sense that we'd want to say, well, now if we only want the lower half of the circle, it's still going through r, and minus r, then we would need to have just the negative square root. So this is the formula for the lower half of the circle, and this is the formula for the upper half of the circle. Sorry, that picture should really be down here. So when you draw it in your book, maybe line those up with each other. Now, when you're asked to graph one of these things, it may be that you've memorized the form and you can look at that and just say, it's a semicircle, got it. If you can, that's fantastic. If you can't though, it's not a bad idea to be able to fiddle with the formula to say, gee, I'm not sure what this graph is like. What can I do to help myself figure it out? Well, a natural thing to do to help yourself figure it out is to say, what would happen if I squared both sides here? And just write it down as working. I would get y squared, and if I squared this side, I'd get 25 minus x squared. Now I can fiddle with that, add x squared to both sides, and I've got x squared plus y squared equals 25. Now, I can recognize this one as a basic circle that has its center at the origin and a radius of 5. So I know that this one that I've been given is a lot like that. But there's an important difference. I've gone ahead and squared both sides, and that's actually changed the graph. Okay, it's made more things possible because this one says that y has to be positive, and it's because it's got that square root on the entire right-hand side. So yes, I've sort of got my circle with radius 5, but I only want the upper half of it. So I can go ahead and say I just want this part. We've got 5, -5, and 5, and you can graph it. Similar story here. You could do the same thing to this one to see that this is a lot like x squared plus y squared equals 7. And that's going to be like a circle that's got a radius of the square root of 7. But this negative that's out the front here tells me that we only want y values that are negative. And so that tells me that I want the lower half of the circle, and the radius is root 7. So I can say this is negative root 7 over here, and down here we've got negative root 7. And it shouldn't be too much of a leap to go back the other way if you're given the graph and you can see that it is a semicircle to come up with an actual equation. Now there's two ways you might do it. You might recognize that basic form of a semicircle, which is like this, where we've got r squared minus x squared. And all you've really got to put in is what r squared is. In this case, if r is 10, r squared would be 100. Okay, but if you haven't memorized that, and you look at it and you go, gee, I think it looks a lot like a circle that has a radius of 10, so r squared would be 100, that's not a bad starting point, because if you've forgotten this form, you can just build it freshly each time. You can say, let's get the y squared by itself by subtracting x squared from both sides, but I can see here it's not actually a circle, it's just the upper half, so I want just the positive square root of that. And you'll come up with the exact same formula with that method. Similar things happen every time we have a square root in our function. So a good starting point would be to acknowledge when you see one of these that this whole section here has to only take positive values, and that means that y has to be positive. So we're expecting our graph to have nothing below the x-axis because every point down there has a negative value for y, and y must be positive. But it also makes sense to say, hey, what shape does this thing have? What is it a bit like? And if you're looking for a graph that this thing is related to, it makes sense to square both sides just so you can see the shape of that basic graph that it's related to. So squaring y, we get y squared. Squaring the square root of x, we just get x. Now, what is this thing? What does it look like? Well, we're already really familiar with y equals x squared. That's our basic normal upright parabola. So this one looks very similar. Y squared equals x. If we write it the other way around, so it looks a little bit like this, what we're saying is that x is equal to y squared. Now, all this does is we've basically swapped the x and the y around from our usual parabola, y equals x squared, to this other weird parabola, x equals y squared. So that means whatever the y-axis was doing here, which was being the sort of center point between the kind of horseshoe-shaped arms, the x-axis is now going to do that. And whatever the x-axis was doing, which is being sort of like the thing the horseshoe was sitting on, well, now the y-axis is going to do that. So this graph is basically just a parabola on its side, and it looks like this. So this is our graph of x equals y squared, which you may or may not have seen before. All right, so this graph that we're trying to graph is going to be a lot like this one, but importantly, we can see that y has to be positive. So if we're graphing y equals the square root of x, we don't want the whole thing here, we just want the top half. It'll be just that bit. And if we're graphing the bottom section, it'll have a negative out the front, and that shows that everything on the right-hand side is definitely negative, so everything on the left-hand side, in other words y, is also negative. And so that would be this part down here, which we can show in red. A better sketch of the positive one here. Okay, it's a rough sketch, but we can see that it's basically a parabola on its side, but it's only the upper arm.